Hello. So today I want to talk about graphing using derivatives. Sometimes it's called curve sketching, right? Sketching a graph of a curve that we might not know what it looks like. Derivatives, in particular, the first and second derivative together, really help us determine the shape of the graph. And here I show the four combinations in this little table of what it could look like. You could have the first derivative being positive and the second derivative positive, which means your graph is increasing and convex. That's the shape that I'm showing here, right in this box. It's increasing and convex. You could have, and some sources call it concave up, just a heads up there. You could have that the graph is decreasing and convex. That's possible, right? In which case they would look like that on that interval. You could have a graph be increasing and concave, right? You could have a graph be decreasing and concave, right? And once again, increasing, decreasing is determined by the sign of the first derivative. Concave or convex is determined by the sign on the second derivative. If the first derivative is zero, possible max and min, right? If the second derivative is zero, that's a possible point of inflection. And what do we mean by point of inflection? It just means a place where the graph changes from concave, this would be concave, right, to convex, or vice versa. Right? So what I want to do now is look at the graph of a function. F of x equals natural log of x squared. And I want to graph this using the first and second derivative. What I've written here is just a little bit of analysis that does not involve derivatives. The kind of things, so sort of just quickly nodding at those on the way to the part that we're really interested in this video, which is using the first and second derivative. So, but you would do some things typically before you even think about derivatives. For example, domain. Where is this function defined? Well, it would be defined everywhere because x squared plus 1 is always positive, right? It's always a positive quantity. If you take a real number, square it, add 1, it's always positive. Therefore, natural log of a positive number is always defined. You don't have log of 0, you won't have log of a negative, you can't get anything undefined. So this is defined everywhere, this function. So the domain is the set of all real numbers. Right? The end behavior, just think about if you plug really large x values in to this function, natural log of x squared plus 1, you're going to get log of something giant. That goes to infinity. If you plug, even if x is negative, we're squaring it anyway. So say x equals negative 10, right? Well, that's going to be log of positive 101. So you still get infinity to the left and to the right. So I know I have some function that looks like this. Looks like it goes to infinity to the right and infinity to the left. But what does it do in between, right? This is the this is about as much as and I know that it doesn't have any holes, so I know it does something in between, right? But what exactly does it do in between? It doesn't have any vertical aspect, it doesn't have any holes. What does it do in between? Well, let's use the derivatives to find out. So what is the first derivative of this function? The first derivative would be f prime of x, right, is 1 over x squared plus 1 times 2x by the chain rule, right? So this is 2x over x squared plus 1. So then I could find when is this positive, when is this negative, right? And when is it 0? So let's see, this quantity would be 0 when, well, it would be 0 if and only if the numerator is 0. So it's 0 if and only if 2x is 0, which is to say only when x is 0. So that's the only 0 of the first derivative. You can then look a little bit further and say, okay, on each side of 0, what happens? Well, this is always positive. This quantity is positive when x is positive, right? But it's negative when x is negative, right? So we just figured out the first derivative. And if you want, sometimes you sum up all that information in what's called a sign chart. It can be a useful way to compile that. So you could say, okay, here's f prime versus x, right? So when x is 0, f prime is 0. If x is less than 0, so down here, if x less than 0, then the first derivative is negative. And if x is greater than 0, then my first derivative is positive. So there's just summarizing all the information below. It's just a nice condensed table to put it in. Now, second derivative. For the second derivative, here, I have to work a little harder, right? I don't get away with just a nice clean little chain rule. Here I'm going to have f double prime. And I already knew the first derivative was this quantity, 2x over x squared plus 1. Well, I'm taking this derivative, I need the quotient rule, right? So I do the derivative of the top times the bottom minus the top times the derivative of the bottom. All of that is divided by the bottom squared. Right? So what do I get? I get x times, 2 times x squared plus 1 minus 2x times 2x all over x squared plus 1 squared, which, if we clean this up, becomes 2x squared plus 2 minus 4x squared, again, over x squared plus 1 squared. So I get negative 2x squared plus 2, right, when I combine like terms on those x squared terms. This then still has the same denominator. And now I can ask, when is this quantity positive, negative, or 0, right? So first, let's think about when would this be 0, right? Well, this would be 0 when the numerator is 0. It's a fraction. Fractions are 0 only when their numerator is 0, which in this case would be when x equals plus or minus 1, right? So those are the two places where this quantity is 0. Now, look at, let's add this into our sign chart, right? So I want to think about x versus f prime and also f double prime. Now I want to think about all of these. So I'm making a bigger upgraded sign chart. And what I just figured out is what? We have some important points here on our graph. I have 0 where the first derivative is 0. I have minus 1 and 1 where the second derivative is 0. Right? So I'm getting some important points here. Then I can also say that f prime was negative over here. F prime was positive over here. Right? I can also then ask myself for the second derivative, what are the signs, right? So what's the sign of the second derivative at 0? We'll just plug in 0 and find out, right? So here I could, like, to know what to put here, just calculate it. I have a formula for f double prime, so just calculate the value, right? So f double prime at 0 is going to be what? It's 2 over 0 squared plus 1 squared is 2, right? So here, I actually don't care about that value 2. I just care that it's positive, because remember our little table, I'm just trying to determine the shape of the graph, positive. So I just want the sign. I don't really need the value. I just need to know 0, positive, or negative for the first and second derivative. So what more can I say here? How about beyond 1 or before minus 1, right? So suppose I look up in, that should have been minus. I don't know why I had a plus there. But suppose I look at another point, right? Let's pick just another point, say 2 or minus 2, just to see what the second derivative is doing. So there, if I plug 2 or minus 2 into the second derivative, right, I actually get the same value either way. It's an even function. And in either case, what do I get? I have minus 2 times 2 squared plus 2 over something positive, right? So I get negative 8 plus 2. So I get negative 6 over something positive is negative. And again, I don't really care about the value. I just care about the sign. So out here, it's going to be negative, right? So now I could summarize all of this information, right? I could say, okay, here, think back to the previous video, right, on classifying extremely using Fermat's theorem on the second derivative. What do I have here? I have a horizontal tangent, right? A horizontal tangent with positive second derivative, meaning it looks like x squared, right? Positive second derivative means I have a min at 0, right? So now I know quite a bit more about my graph. I know it has a really important point at x equals 0. So let's plot that point. So f of 0 then is natural log of 0 squared plus 1, which is 0. So I just figured out from that little chart that my graph has a min at 0, 0, right? So there I have a nice important point on my graph. So there's a min at 0, 0, right? And I also know that the second derivative was positive, so it's going to be convex at that point, right? And where does it change? Well, it changes right here. Here, so I'll put this in green, right? This is that point of inflection. Now, or sorry, that min, right? Now here, notice here, the graph changes from over here. It used to be convex, but it changes to concave, right? So there at 1, we're going to get an inflection point. This is a point of inflection. This is also going to be a point of inflection. Here it changes from concave to convex, right? So that is where I can find 2 points of inflection, right? Right, so here, whether I plug -1 or 1 into the graph, again, I get the same value. This is going to be -1 squared plus 1, or 1 squared plus 1, same value, right? And either way, I get natural log of 2. So here, I'd have the point of inflection at 1 comma log of 2. Or here, I would have a point of inflection at -1 comma log of 2. So the graph will switch concavity and look like this. So switch concavity and look like this, right? And now I have those intervals right here. You can see those cases. Here I have increasing and concave on this interval, right? On this interval, I have increasing and convex. On this interval, I have decreasing and convex. And on this interval, I have decreasing and convex, right? And those are exactly those 4 cases all stitched together to assemble a graph, along with our end behavior, right? Notice it's going to infinity up here and infinity on over there. So there now, not every graph has to use all 4 of those cases, but here, of course, I wanted to show an example that does use all 4 of those cases. Notice we're just assembling the information on the sign of the first and second derivative to get all this assembled and get our sketch of the graph. Great. So there we go. There is the graph. The graph of a function that would be pretty hard to graph in pre-calculus, right? Natural log of x squared plus 1. We got a pretty accurate picture of it. Thank you.